Okay, so in this video we're going to talk about coupled reactions. And so in the last video we mentioned, we briefly touched on delta G's and KEQs and the relationship between favorable and unfavorable reactions and their equilibrium constants. So let's have an example of a reaction that is unfavorable. Let's just say that we have A turned into B equals a delta G naught of, I don't know, plus 5. Okay, so this is an unfavorable reaction and one that's not likely to occur, obviously, unless given an input of energy because it's endergonic. Well, what can happen is if A to B with a delta G of plus 5, you can couple this reaction if you take B and convert it immediately to C, and let's say that this reaction has a delta G equal to minus 7. So the conversion of B to C is more favorable than the conversion of A to B. Okay, so the coupling the conversion of B to C to the reaction of A to B actually makes an overall reaction, A to C, equal to a delta G naught of minus 2. Okay, so that means that now we can turn A into C by way of B, all right, and make this now a favorable reaction. So unfortunately, what this means is that we can turn A into C, right, through this way, but we end up with C. Well, what if we actually wanted the molecule B? Okay, we still are at a problem where we can't get this molecule made because it's got an endergonic reaction. So one way to couple reactions is to convert the product of the unfavorable reaction into a product of a favorable reaction. So by converting B into C, we can now overall make this delta G's a favorable reaction. And the way you add this up is it's just simply additive. So you take the delta G of the first reaction plus the delta G of the second reaction, and this is your sum, -2, and that tells you now that the overall delta G of these two reactions, okay, is favorable, meaning that this is most likely to occur spontaneously, or at least it's exergonic, releasing energy. But again, let's go back to the question: what if we still wanted the molecule B? How do we couple an energy favorable reaction to an unfavorable reaction and still end up with the product that we want? And so this is where the role of energy carriers comes into play. So energy carriers, and these are molecules that carry high energy electrons on the molecule that can be transferred to other molecules. So the most classic energy carrier that we talked about in class is ATP. ATP can be converted to ADP, all right, and inorganic phosphate, so PI. Okay. And this has a delta G naught of roughly minus 7.5. I forget the exact value, but for this it's okay. So what can happen is if we want to go A to B, which has a delta G of positive 5, okay, we can couple A to B to the hydrolysis of ATP, which releases a delta G of negative 7.5. If you take the sum of these two, you'll get a negative 2.5. Okay, so therefore you'll make this reaction favorable. Well, how do we couple the hydrolysis of ATP to actually end up with B? How do we make that favorable? Well, this uses the property of what we call high energy intermediates. Okay, and I'll draw out what I mean. So if we take A, okay, and what happens is we couple it to the hydrolysis of ATP, but in this sense, the phosphate of ATP, okay, this inorganic phosphate, this is the high energy. This contains high energy electrons that are now transferred. Instead of just being released to the cytoplasm or to the water, they're now transferred to the A molecule, okay? And this is our high energy intermediate right here. All right, so we'll call this HEI, high energy intermediate, and that's what this A phosphate is, HEI, high energy intermediate. What that means is that we had a certain free energy value for this A. Well, when you transfer the high energy electrons to the A molecule, we've actually increased its free energy. Right? And now we have a high energy bond, this phosphate bond, that was once part of ATP, but is now part of the A molecule. And now this A molecule has a higher free energy than it once does, which means that now the conversion of A to B, okay, can be done by using the energy contained in this phosphate group. Okay, so instead of releasing the energy from ATP hydrolysis into the cytoplasm or just as heat, the energy from ATP hydrolysis is transferred to this molecule, and now we've changed the enzyme kinetics so that this reaction, A phosphate to B, is now equal to a delta G, right, of basically minus 2.5. So the way we can draw this in a more simplified version is that A to B and ATP to PI and ADP equals a delta G naught of minus 2.5. Oops. Okay, minus 2.5. All right. And the reason why this can happen now, we still got our final product, even though this one was unfavorable, but we used the high energy bonds of ATP, transferred that bond to the A molecule, made it a higher free energy than it once was, which now gave energy to catalyze the reaction A to B. Okay, and next week when we talk about glycolysis, you'll see why this is needed, but the input of energy from ATP will help drive unfavorable reactions, okay, to occur. So this summarizes briefly the purpose of coupling reactions in two ways. You can couple it by converting the product of an unfavorable reaction into the product of a favorable reaction. However, we're going to end up with a product that you might not want. But if C is what you want, you can actually start with A and turn it into C and make this favorable. The other way you can couple reactions is by using energy carriers, and these are molecules that can rotate like trucks and transfer energy from themselves in the form of high energy electrons and transfer that energy to molecules in the form of high energy intermediates that can then be used, the energy can then be used to drive unfavorable reactions. So I hope this cleared up coupled reactions for you. Again, if you have any questions still on some of this, or maybe if I confused you anymore, hopefully not. But if I did, please email me over the weekend or come see me Monday and we can go over this again. But the point of coupling reactions is essentially to take an energy favorable reaction to drive an energy unfavorable reaction to completion. And there's a couple ways to do it. But what I want you really to understand is how to add the delta G's. If I ask you, could a reaction with a delta G of -7 drive a reaction with a delta G of +5? The answer would be yes, because the overall delta G would be -2. Okay, so you can kind of practice the addition yourself.